We're here in lovely, rainy Southern California. Wishing we were in Palm Springs with you guys, but it happens. But I'm here with Christian, and we're going to talk to you about best practices for building web apps that visualize large data sets. Just to set the mood, we're in this very tiny room. I kind of feel like Click and Clack from NPR. We're going to talk about cars. But we'll see how well this goes. Okay, so best practices for building web apps that visualize large data sets. So we'll do just some initial considerations. We're going to talk just a few minutes about what the JavaScript API and the ArcGIS platform do for you, and then give you some optimization, both visualization techniques, so scale-dependent filtering, clustering, and data prep and processing, reducing the generalizing features and attributes, and aggregation. We won't have an aggregation demo, but we'll talk about it a little bit. Anything you want to add here?
No. Yeah, let's just dive right in.
All right. Considerations before we start. I think this is pretty obvious, but it's always just to think about it, is you need to know your audience. Who is your app for, and what are you trying to show? Is it for just a few specialized users? By a few specialized users, if you have if you know that audience, if you know those specialized users want to look at your app, and they're going to be looking at it from a desktop, that gives you some hints there. Or if you know that the specialized user only looks at things on the phone, you have to change your tactics. It's worth thinking about whether this app is public or private. If it's a public app and you build an amazing app that gets picked up by CNN, might have some different things to think about and how well that works when it goes viral. And that is something always to think about. What's the potential to go viral? How many people will be interested in this app? You can follow what we talk about today, and I think in a lot of cases you can build apps that go viral. You just really need to kind of watch out for how are they going to view that when it goes viral. Typically, when something goes viral, it's really viewed on the phone, and so you need to think about that when you're talking about showing off big data. So desktop only, mobile versus tablets. Generalization is very important, and then Christian's got a lot of good examples of this. From choosing what's the right type of geometry to use, how do you reduce the number of features, how do you reduce vertices. The platform does quite a bit of auto generalization for you, and I'll talk a little bit about that. But in some cases, you may need to go further. Okay, and we'll go behind the scenes. All right, behind the scenes with the JavaScript API. So just want to talk briefly about what ArcGIS Online in this case does for you, and some of it also applies to enterprise. Well, ArcGIS Online is a platform for sharing important information at scale. So I see these different apps here, the Sonoma County fire app from last fall, the COVID-19 dashboard from Johns Hopkins, the City of Tampa flood warnings, to Centers for Medicare and Medicaid Services giving out Medicare Part D opioid prescribing mapping tool. These are all apps that might receive many thousands of requests per second or have millions of concurrent users. So how do we make that scale? So keys to efficient public sharing of data-driven maps and apps at scale include, requesting data as tiles. This is probably the most important thing. This allows multiple tiers of caching to get used. So tiles, data that's easily shared between other users. Of course, there are things like raster tiles and vectors tiles, but in 3D, there's I3S tiles. And mostly what we're going to be focusing on today is this next point, the dynamic feature tiles. They're generated on the fly, they automatically handle data updates, and I'll show you how that works. The JavaScript API queries are common, and they're identical across different users and different applications. Why is that important? That means that we can cache those results at multiple levels within the system. We can do response caching, So server and ArcGIS Online can create a response cache of the queries you're making for improved performance and scalability. Or the CDN, or the Content Delivery Network, can cache data at the edge. So when I'm, for public content, when I'm accessing data from my machine, I want to go to the closest CDN node as possible to minimize that network latency. And then, of course, the API is really great about taking advantage of client-side queries and analytics. Once you retrieve that data, you have basically a full database that you can work with the data in memory. And it leverages the power of the machines. I'll just do a little bit more on the feature tiles. It's an efficient, flexible, and scalable way to bring data to the client. So this example of building footprints in New York, we've got 940,000 polygons. This actually loads a lot of data. But how does it load it? Well, it queries for the data one tile at a time. So if we were to take a look at this big tile here, that's actually a 512 by 512 pixel tile. And it's going to get all the features that intersect it. Now, if I look down to the 512 by 512 tile below it, I see that there's quite a few more building footprints as I move to the south here. And it's going to not be able to get all the features in that one tile because it is limited to the server's max record count. So it's just going to get, the server is going to say, hey, you can't get it all. And then the client's going to subdivide it and make a smaller request. And then it'll keep making smaller requests down to 4 levels of request. We call this our drill through. What's important about this is that we're requesting this data in an efficient way that can be cached, but this is still a lot of data. So getting back to your audience, if this is definitely not something that would provide a good user experience on a phone, for one thing, you're not going to be able to get this regional view of that data that we want here. And this thing animates through if you were to look at this sample in the SDK. So you really have to know who's going to view this and what's the most important thing to show. In this application, it's showing when the homes were being built. I'm not going to, just a little bit. We request the data in a certain way. We request the data to come back in protocol buffer format, so it's super small. It's the same thing that Vector Tiles uses. We query based on tiles, so it's envelope query. We only request the fields that we need. So in this case, it's rendered on the year field, and I also have the object ID. I'll drill into this more in a second. And we quantize or generalize the data so we get no more than 1 vertex per pixel. So at this scale, the tolerance on this quantization is 38 meters. If I were to zoom in one, it'd be about 19 meters, and so on. And then finally, we tell the server that it is a tile request and it should be cached at different tiers. When it comes back, main thing to call out here is that the sizes are pretty small and the times are pretty fast. And in a lot of cases, since this is public, it's getting a hit from CloudFront, so at this EDN. And it's also cached at feature tiles. Just to give you a little look behind the scenes, the data structure returned from the feature tile query is highly efficient. So this is the JSON version of a protocol buffer response. And I see that if I look for this single features polygon, in this case, it was constructed in 1925, it actually has on its one ring 4 vertices. And it just has the starting point. And this is with respect to the translation coordinates, so the origin that's specified from the quantization. And then it just offsets. So why is this important? Well, we want the number of digits to be small. We don't want the full double precision digit. Since we quantize it to 38 meters, it now snaps it into this integer view from this location point. And we know how to turn that back into real world coordinates and map it. Once it's there, we process it, triangulate, and prepare for the features to be drawn on the graphics card. We do a lot of work on line optimizations. We want to balance the display quality with overall performance. So if I look at this graph here, the memory requirements is the y-axis and the processing time is the x-axis. And this is the actual line that I need to render. This is the actual geometry that I need to render. Now, if the size of this geometry is less than 2.5 of this line is rendered at less than 2.5 pixels, then it always uses this quad format. And it's the smallest number of triangles. It's got 8 vertices and 12 indexes. So it's very low on the processing time and relatively low on memory requirements. And if you were to look at it really closely, you would see that it's actually not butting up against each other or joined. But based on research that the team did, this basically means that in most cases, you can't really tell the difference at this size.
Yeah, it doesn't look pretty, but it doesn't matter when it's that small. You can't really tell a visual difference.
Yeah. Exactly. And then if it's bigger than that, then based on which join type you have, we will render that as you described, but each one comes at more of a cost. As you can see with the round joins, it adds a lot of triangles. That's a lot of processing that needs to happen and a lot of memory that needs to hold. There's probably too much detail for this session, but just to give you a sense that the API is trying to do what it can to get the best possible performance. And that performance has improved dramatically over the last year. 32% faster load, improvements to speed and accuracy and memory, improved how we triangulate, and we have faster lines. So let's do a quick demo of that. Okay, so this layer I've got here. Let's see, it's okay. I see that it's this zip code layer. It was last updated at 232. And I'm going to reload this page. Hopefully we still have the internet. And I've got my network requests here. There we go. Okay. I'm going to pull this out just a second. So, a couple things. First, the map is drawn, but these are the queries that went into making that map get drawn. I see the sizes are relatively small. Well, that's because we are generalizing that geometry to a 611 meter tolerance. So we're quantizing to that level. Notice we only requested the object ID, but it's a miss from CloudFront and it's not cached within Esri. Now let's go back and just do that again. Okay, so same set of queries were executed, exactly the same, but notice the times were much faster, all around 600 milliseconds. And notice that this feature tile cache turned to true. That's because the server had a version of that query already cached. So it didn't have to go back to the database. It didn't have to quantize the data after it got the data out of the database and package it up and send it to you. We could just pull the response out and send it. Now, if I go back and make a change to the data, just make one edit here. Oops, didn't actually make the edits. Now I notice that the last update is 313. And let's reload the page again. And we'll see that the queries are a little bit slower. I see that most of them are over a second, and they're not feature tile cached. So that's the dynamic part of the dynamic feature tiles. As your data changes, these queries are up to date. Now let's see what happens when we make this layer public. Back to overview, share to everyone, and reload the page again. Okay, so I see that the times were pretty good. It's still coming from that feature. Now it's coming from that feature tile cache because this is a repeated query back to the server, and the data hasn't changed in between that time. And the times are, in the 200 to 400 millisecond range. But let's do it one more time. Notice that I'm not sending a token this time. So it's a public layer. So one last reload. If our internet holds. Okay, I see now I got a refresh hit from the CDN. I'm going to do it one more time. Not always guaranteed to get a hit from the CDN. There we go. Now I see that making the same request, it's still cached on the server, but now it's cached at CloudFront. It's cached at our CDN. And you notice the times went down another order of magnitude. So this is very important for you to get optimal performance. You can also control this for public content by changing this. If your data doesn't change like zip codes, I would just change it, set it to an hour. That means you're more likely to have people hit that data from the CDN. So this is all just general performance tips, or what general performance, give you a general idea of what's happening behind the scenes so that we can deliver complex data to you. But now, if I just go back to this and see that I only requested the object ID because I'm not rendering on anything. Let's make a change and let's do a filter. I'm going to add an expression, and let's say I want to do this Zillow housing estimate, and let's see here, what's going on? Oh, is, sorry, is greater than, doing it wrong. Okay, well, how does, see, I get fast performance, this happened on the client side, but how does that work? I only had the object ID there. Well, the map viewer, the new map viewer is written with the JavaScript 4 API, but what it does is it requests the data for you smartly. So when if I were to look in the code of the map viewer, they did a layer view dot filter, and that filter was based on that Zillow housing value index field, which is a ZHVI. And what the API did is it made another set of tile requests, did not return the geometry, just return the object ID and the field that I was working with. One last thing to look at is now that I use that Zillow housing index for filter, when I zoom in, it's actually still going to remember that I'm using that field and include it on the next query. So I'm requesting the Zillow housing index. I'm getting the geometry back, and I'm passing that filter to the server. So this is all happening under the hood. So you can just specify, basically, when working with dynamic feature tiles, you can work with just the fields you need. And then if later your app decides that it needs to work with another field, like doing a client-side filter, or maybe you're going to render on that field, it can page that data in and update it seamlessly. Now there are cases where you don't want that and you want to have all the data up front, and Christian's going to show you that later. Anything to add on this, Christian?
No, it's awesome. It's cool to see what the ArcGIS platform does to make it to increase the efficiency in bringing all that data down to the client.
Yep. Okay, so the platform API is doing our part. Now, I think we're going to give you some ideas on what you can do for your part for handling this big data.
Absolutely. Thanks, Jeremy. That was an awesome rundown of what the API and the platform do for you. That also doesn't excuse you from not doing your part in improving the performance of an application. Certainly doesn't mean that there is no limit to the number of features that you can bring down to the client and work with. So I'm going to start diving into some of the visualization techniques you can do to help improve your app performance even further when working with lots of data. And really the first thing you can do, or one option, is doing filtering based on scale. And so to illustrate how this works, or what the benefits are of this, I'm going to show you this layer of water distribution pipes in Bangkok, Thailand. So I'm going to go ahead and flip over to this application. And now you'll see rendered in the view this line layer, visualized with these bright pink lines of pipelines. If you look over here, you'll note that this isn't a small data set by any means. It's bringing down 18, almost 19 megabytes worth of data.
On that, Christian, that's the raw data.
That's the raw, yep.
So the 8.4 megabytes would be the compressed size. But that's a lot. 8.4 megabytes is a lot for a web page to download. So you're gonna, people are gonna potentially be waiting for the data.
Yeah, even in the desktop, definitely on mobile, this would not work very well, would it? Mm-hmm. So one thing that we get asked pretty frequently is, how many points can I render in the view, or how many features can the API allow you to load? And really, there is no one solid answer to that question, because it all depends. As Jeremy mentioned before, it depends on your audience, your users, your devices, and ultimately what the browser can handle. So one of the follow-up questions I like to ask is, why do you want to render so much data in the view? And if you look at this particular map, we've got a lot of pipes here. I'll show you how many there are exactly, but does it make sense to render all that in this particular view or at this scale? So if we look at the item page, let me go ahead and right here. Okay, you'll see that this is over 500,000 features that we're working with, and a number of fields. And that particular layer only needs one attribute, that's the object ID field. So I'm not bringing all of these features down, but this is a lot of lines. This isn't just points, but each line obviously has some vertices that we're working with. So what are some things that we can do to improve the performance? Particularly like this next slide, I ran a few filters on this data to see how we could improve performance and how it impacts the visual. So if you look at the image off to the left, you see this is what we just looked at. There's no filter set, got about 18 megabytes worth of raw data. And on my desktop, using a fast network, it took about 7 seconds to load that data after taking advantage of the tile caching that Jeremy just described, amounting to more than 550,000 features in total. So you may have noticed when I showed you the data tab on that layer that there is a field for the pipe size. And for line data and point data, there's often, especially when we're making data-driven visualizations by numbers, there's some indicators that we can use to filter out data that doesn't make sense at the smaller scales, basically when you're zoomed out. So in this particular case, we have the pipe size. And so in theory, the wider the pipe, we could think about it like a water main. You'll see, if we compare it to a highway or road system, there are fewer of those, and they may make more sense to view at these smaller scales versus every tiny little pipe that we can fit in there. So just by filtering it out by the pipe size of 150, I'm not familiar with the units, they're in Thai, so it wasn't, but it basically ranged anywhere from 0 to 400. So I chose 150, and that immediately filtered out nearly 200,000 features. And you'll notice, based on those images, that you don't see a whole lot of difference at that view. So, it reduced, of course, the amount of data brought down to the browser, and it was therefore a little faster to load. Now, mind you, it's still a lot of data to work with. So I decided to bump that up some more and take a look at filtering out pipe sizes that were 300 or larger, and still improved the performance on that, but it's still a lot of features. It was about 100,000 features or so. it is a lot smaller than what we started with, and the visual is actually a lot nicer in my opinion.
Yeah, I was just going to say that visual is way nicer. Otherwise it just looks like a yarn ball.
Yeah, you get a sense of where the data is without totally overwhelming the user with this pink blotch.
Yeah.
Right.
I guess the other thing, that's you on a desktop on a fast network, 107,000 features. My guess is that on an old phone, it's probably not going to work very well.
Right.
So that's something you really have to know, like back to the beginning, what your audience is, what they're going to view it on, and what's going to be the best visual for them to be successful, or the best visualization for them to be successful on the device that they're looking at it.
Yeah, that's a good point, Jeremy. And one of the things that might be a question is like, how do I know what looks good at a particular scale? With line data, while working with this, I just think about road networks. And let me show you the code really quick for this application. So here I'm bringing my layer down, and I'm going to show you some of the techniques that will make this easier to work with. But let's go ahead and remove the layer from the map for a second and just look at our base map. So this is a street space map at night. So make sure I got my data. There we go. So notice that as you zoom out, you don't see those roads, those buildings anymore. You just see the main highways, and a few come in as you zoom in. May seem like basic cartography or GIS, but it's something important to remember even when working with these dynamic feature tiles. Just basically wanted to follow the same pattern with the pipes. So when I add that, I want to filter out that pipe size that's greater than or equal than 3,000 or 300. And also, I think setting a min scale is important because that allows us to not display the data at scales that don't make sense. So right there, I couldn't see any data because of that min scale, and now all that data comes in as I zoom in. But as I zoom, sorry,
could you just could you reload the page one more time?
Yep.
And then
zoom in.
Okay, now clear your. Oh no, okay, that's good. So yeah, that was 1.5 megabytes of data that came down for that view. So you really reduced it a lot.
Yep.
That's nice.
But obviously you want to get more detail as you zoom in, and just setting a static filter isn't going to accomplish that for you. So I'm going to enable this code here. All I'm doing is I'm setting a watch on the view for the scale property. And by default, I'll set that definition expression to null. So if it doesn't meet any of the conditions, I'm going to display all my data. And again, these scale values may feel arbitrary, and I'll kind of show you how I came up with those. But if I start to zoom in, I want to bring in those moderately sized pipes. Sorry, if I'm zooming out, I want to only filter based on the moderately sized pipes. And then as I zoom out even further, only those larger ones that you see in that view. And then I'll only set that definition expression if it doesn't match the previous one. So now I've got a dynamic filter on my layer. So don't see any data right now because of the view scale. I go in one level and we'll see those pipes that are 300 or more. And then as I start to zoom in some more, you see more data come in. And this level probably won't have the highest level, but as I zoom in further, you'll start to see some of those smaller pipes come in.
Mm-hmm. I'll probably still would have moved it in one more level because it added a lot than at that first zoom level where the scale kicked in. But yeah.
And so you'll see some of these features are pretty small, and I just wanted to highlight one of the cool visualization techniques that our API offers is that as you zoom in, you note that these line widths are getting a little larger. They're easier to see. If I don't change the size of those line symbols, they become almost invisible, especially with this type of base map with bright colors that they tend to conflict. So you get a nice little visual as they grow.
That's a great point. Yeah, what Christian's saying there is that as you zoom in, we'll draw a bigger line, and as you zoom out, you'll draw a flat line. And typically, if you're viewing that whole city, you're going to want those lines to be as small as possible. And so you make it really small, but then that just doesn't carry along as you move in. And, well, how would you do that in ArcMap or Pro? Well, you'd create multiple layers and you'd set up their definition expression and their color, and set the visible scale range so that the layers turn on and off. But what Christian's here is doing that in code to set the definition expression based on watching the scale change. And then the line thicknesses is handled automatically for you by the API.
Yep. And this is how you do it. You just set a size visual variable and you set a pretty simple arcade expression. You just want to watch the view scale inside the renderer. And then based on these very small scale values, you're going to change your width, because when you go beyond that scale of 9,000, it doesn't really make sense to show any thicker lines than that.
And so the two of those scales are less than 2 pixels in size. So based on what I showed earlier, we would always be drawing the most optimal line butts.
Right. Yep.
And you could definitely not tell.
Yeah. And so Jeremy noted that one of the scale values didn't necessarily make sense. So something that I do is I just log my scale in the console. So you see that there. And so was this the level that we saw data come in at? Yep.
Yeah. And it was a little bit slower too.
Yeah, so we should probably go in a little more like maybe here.
Yeah.
Let's grab that scale value and set that as our limit here. And then
maybe make that like 16 or something.
Yeah. Let's do that. Okay. Zoom in. So that's the original resolution we had. And we go in one more level, we get more data, I believe.
I think it's one more.
One more than that. There we go.
Yeah.
Yeah, so that looks a lot better.
Yeah.
And as you zoom in, you get those other features.
The full thing. Very cool.
And so that's using attribute data. You can also kind of piggyback off the idea off of the quantization parameters that Jeremy was showing earlier, and perhaps use the view resolution. You have that resolution parameter on the map view, and be a little more aggressive. So instead of only rendering one vertex per pixel, you could say, I don't want to render the features that are longer than 2 pixels or 3 pixels. And you actually filter out a lot more data than we did with those attributes. We got all the way down to 62,000 features by going by an order of 2 on the view resolution, and then even 30,000 features by an order of 3. But you see, as you increase that resolution, you definitely will take a hit on the visualization. You see a hole sort of forming in the middle of the city there. So that may not be desirable. I may stick with the original visualization of just filtering out those smaller features.
Yeah, I'd say definitely if you know your data well and you know something that makes sense to not filter on at certain scales, then that's the best approach. I think the view resolution, basically reducing features that are less than a certain shape, is kind of a blunt tool. You don't really have any control over that, and you might be losing important things like downtown Bangkok.
Yes.
Yeah.
Yep. Yeah, and you can check those queries too. If I look at it here, this is the same app, and I check my filter in my query. See that I'm filtering based off the shape length, and it's by an order of 3 off that tolerance, or 2 actually.
I think one thing to watch out for with shape length is it's not guaranteed to be meters. It's whatever the source.
That's a good point. Yeah.
Whatever the source data was, projection, it'd be that unit. So I think it's something to watch out for.
Yeah, absolutely. So you got a number of ways that you could filter it, but as Jeremy said, get to know your data well, and I would take advantage of filtering by scale without, and that prevents, you don't even have to use multiple layers in that case. You get to work off the same layer, and it keeps your app clean, and your users happy.
That's right, yep.
All right, I'm gonna go ahead and pass it back over to Jeremy, who'll talk a bit about clustering.
Clustering. All right, cool. So that was great, Christian. Like you said, you're reducing the amount of data you're bringing down based on some smart choices. Once you've got the data down, this is more definitely for points. Let's just say with points, you can add lots of points. You know, a point is very simple geometry. It's just got an X and a Y. It's not like a line or a polygon that's got a number of vertices and the complexities that come with that. But if you throw a bunch of points on each other, you know, you're not going to have a very pleasing visualization. So let's look at this example. This is using the city of Eugene. They've been collecting tree data for a while, and they have about 5,000 tree points. And data is pretty impressive. Oops. Let me zoom in, sorry. The data is pretty impressive. Oh, I filtered out the pop-up here, though. Well, I'll show the data in a little bit. But I can't really tell much from this. Now, at the scale of here, I can get a pretty good feel for the trees and where they are. It makes more sense, right? But at that zoomed out scale, it's too much visually. So something that has been added to web maps and then also is in the JavaScript API is the ability to cluster. So I'm just going to show you this from the perspective of the map viewer, but the APIs for doing this is very simple, and you can look at the samples in the JavaScript SDK. Just by turning this on, I see that immediately the data gets clustered. And I have control over how much clustering I want. So do I want a high set of clustering or a low set of clusters? Let's get into the style. The clustered cross not really working for me. And I want to change it to, let's say, a circle. Also, this is had a unique value renderer. So what it's showing when it clusters this data is what's the most common tree within that cluster. Now let me go back to the clustering view. And if I move this now outside, let's look at the legend here. You know, I can see that the maple big leaf is the biggest cluster of trees in this area. That's way too much clustering. So I got to find the sweet spot. I usually am a little bit to the right of the low myself. I find if you go cluster all the way to low, it's too much, and you're missing the benefits of clustering. I don't know if you can tell, but as I'm clicking, this is recalculating the cluster. So it's very fast, happening completely on the client side. And you get a pretty good idea of what's happening in Eugene. Douglas firs to the south, maple big leaf in downtown. Outside, I've got red maples. I've got some Oregon ash and sweet gum and the Oregon ash. And as I zoom in, of course, this is scale driven, so I'll get a different view. This is just an altogether more pleasing view of this data set than just looking at all the raw points. And with the clusters, you can also do not just like most common, but you can do other things like, let's say I want to do height. I should say that the size of the circle is telling you the number of features that are in the cluster. Now I'm doing it by height, and so I can get the clustered view of the city. Let me just close this thing out here and zoom out one more. So areas in Let's do above and below theme, actually. And pick one of these other ramps. Flip it. There we go. So areas in red are very tall trees, and areas in dark green are very small trees. Oh, this one's probably better, actually. And reverse it. There you go. So areas in red are very tall trees, and areas in blue are very small trees. And you can add other information there. It's just an altogether more pleasing view of this information than looking at something like, I turned it off, this. Really don't get a good feel for what's
It's
going on
hard
in
to
the
see
city.
the patterns there, yeah.
Exactly. So it's all about the pattern and what's going to work best for your users. So I think this is definitely a great way to reduce the complexity of the visualization of the points that you have, even if you have lots of points. So it's definitely a great thing to watch out for. And as you zoom all the way in, the API eventually just draws an individual feature. Like this is an individual feature, whereas this one right here is a cluster that represents 37. Anything else on clustering?
No, I think you covered all the high points there.
Okay. And then, data prep and processing. Yep. So another point what we'll talk about for data prep and processing is it's sometimes better to move away from polygons and move to points. So if I go back to this zip code data set, and let me switch this, let me clear this and zoom out some. Now notice these queries that are going to come through. It's taken a little bit longer. Queries are bigger. This is taking longer because it's the first time I've been to that area. But I'm starting to get some pretty large query responses here. 150K, 2.3 megabytes actually for this view. That's a lot. So let's clear this out. Remember that number, 2.3 megabytes. I've gone ahead and created another layer which has the centroid of each zip code. And so if I turn that on, boom. Saw how fast that was? That's because it loaded 91 kilobytes of data. And even though those are all misses, hadn't been feature tile cached and it wasn't at the CDN, I think this also has a token, so it's private data, so it wasn't at the feature tile cache. Those numbers are still pretty good even for the first time. And you get a pretty good view of the area, and especially if you're going to end up, symbolizing your data based on, let's say, size anyway. If you're going to render your polygons based on size anyway, you don't get a lot of benefit by adding those boundaries at this scale. Of course, as you zoom in, you could get more benefit and turn on that on the actual polygons as a background. But just by changing the geometry type from polygons to points can greatly decrease the size of data you're actually bringing back.
Yeah, and cartographically speaking, when you're working with numbers like housing estimates, you don't want to be using a fill,
right,
like a color anyway.
Exactly.
So.
Yep. So that's just something it's worth keeping an eye out for to try that out. One last thing before I turn it over to Christian is that there is this optimized layer drawing. So this is for polygons and polylines. So any polygon layer and polyline layer that you have in ArcGIS Online has this option to optimize the layer drawing. This will speed up the initial query, so the cached feature tile query for your lines and polygons by pre-creating a set of generalized or quantized geometries. If you've got line data, it's a quick win because that's going to make that initial query that much faster. If you've got polygon data, it can be a win, although there are some caveats. So polygon layers that are sort of random polygons all over the place and they're not next to each other, it's a great feature. But if your polygon layers are coincident, like let's say county boundaries or zip code boundaries, and you basically turn off the outline, like when you zoom out, you don't want to see the outline, you turn that off, it may introduce some slivers. It's an area we're trying to make better, but that's kind of where we are today. So if you notice that your initial load before the feature tile is created is too slow or a little slow, that is a way to improve that performance. And I'll just say that you can, even for a simple data set like counties, I can download counties from the Census Bureau at a resolution or where the shapefile is like 1 megabyte. Or I can download the same counties data set from the Census Bureau in its source resolution where the size is 300 megabytes. And so that means it's got a lot more vertices describing each county. Knowing what your end result is should help you decide which data set is best to use. Now, we help take care of that by generalizing on the fly, quantizing on the fly, and so on, but it can be really slow to do that initial quantization. This is where optimizing the layer drawing can be helpful to you because it will pre-create different quantized resolutions of geometry and keep them up to date in your layer.
All right, cool.
All right, let's turn it over to Christian.
All right. I just want to continue talking a bit about this data prep and processing and really sort of bringing all these concepts that Jeremy and I have discussed together in one comprehensive example. This app that we created in the process of just a few days, really, that I think is pretty cool. So I'm going to go ahead and describe that app to you. So Esri provides openly a very large data set called Ecological Marine Units. It's basically data that covers all of the world's oceans, and it contains a lot of attributes that we can work with, including salinity, temperature, phosphates, oxygen. And this was a collaborative project from all sorts of organizations such as NOAA, NASA, the USGS, NatureServe. They all provided data that we could use and provide for you to use as well. So I was very interested in this project and started playing around with the data a little bit. And then Jeremy came by, was like a week or two ago, and suggested, hey, we should try to render this EMU data in the Spillhouse projection, which we just added support for in ArcGIS, and see how it looks. So this is an image of the projection, and over the course of a few days, with the collaboration of a few people, we were able to create this application called One Ocean. And just to demonstrate what it does is I'm bringing in some points from that EMU data and visualizing it based on a couple of attributes, salinity and temperature, to name a few, and configured this app so that as the user hovers their cursor over a point, I'm going to execute a client-side query for all of the values of the selected attribute. In this case, it's salinity, for every depth level that we have available to us, and I'm going to render that into this scatter plot off to the left. And so you can see how that profile changes as you go down in depth. And you can see that this actually performs with very fast performance. I like this temperature view. It's got nice vibrant colors. Can you continue to explore it? But then you can also add some more variables such as velocity and direction for each of these points, and that will show patterns of ocean currents. And zoom in, and we can see how these ocean currents move in a particular direction in this area. But something that I found very fascinating is I learned something new, and that's that ocean currents can actually go in different directions depending on the depth. So in this equatorial region, you see that it completely reverses direction as you move down in depth. And also note how fast we can update this visualization as we move that slider. Just for fun here, I added this filter tool that allows you to filter the data that, similar to what Jeremy was showing in the map viewer application there. But this is filtering by geometry, so you can see areas within a certain distance of the line and render that in a matching histogram, so you can explore the data, play with it, explore it by depth, and you get some very fast performance. So pretty cool application that we built with this EMU data, but it wasn't easy initially to work with this data. So I just wanted to step you through the process of how we're able to work with all this data. So I said Esri provides this data openly, so you can go to this ArcGIS Online item and download all the data for use in ArcGIS Pro. But something that may not be immediately obvious is how huge this data really is. It's over 4 gigabytes, which is obviously not going to be usable on the web. And so immediately we had to get to know this data as well as we could. I had worked with it before. I tried it out in 3D views, but this image you see up to the right is an app that loads about 100,000 of these points, which is very small compared to what the whole data set is, which is more than 52 million in total. So just to let you know how this data is, it's 52 million points, more than 4 gigabytes worth of data. And the way it was created was it basically came from a grid that is placed at where the resolution of the cells were every quarter degree of latitude, longitude throughout the world's oceans. And there were z-values involved, so up to 102 different depth levels depending on where you're at in the ocean. So imagine points covering all of the oceans in the world at a quarter degree intervals, and then 102 levels of those points. That's how we get so many. And then on top of it all, we have a number of attributes at our disposal that I mentioned to you before. You already saw temperature and salinity in that app, but also a bunch of others. The new data that Esri created in collaboration with those other teams was those EMU clusters.
One thing before you move on, Christian, the 4 gigabytes of data, you may be thinking, oh, that's not that much data, it's not that big. But remember, our end audience is a web application, so that's a lot of data for a web application. I mean, that's for sure pushing the envelope. Because you saw how fast and interactive that app was when Christian demoed it. That's because he pulled all the data down and then let the browser's CPU and memory handle all that data and then interactively work with it in memory. So this is probably the most extreme example of a web application that's pulling a lot of data down. Now, it's not pulling down 4 gigabytes, is it?
No, we had to definitely do our part. Where the API is not gonna or the browser's not gonna handle that for you.
You're not gonna go to a website and wait for it to download 4 gigs.
Right, yeah. I've already probably tried that at one point and failed miserably. So the goal, as Jeremy said, is you got to get that total download as small as possible. And I know the title of this session is working with large data sets, and this is a large data set, but it doesn't mean you should bring it all down. It's about making it usable and workable with your application. So the first step is it's generalizing the data or filtering it or thinning it out. So we already know that we have up to 102 levels of data, and since we're working in 2D, we don't need to have 102 copies of all the points essentially. So the goal is let's create 1 point per location and then create a flat table. And the way you can do that using the ArcGIS software is you could do a spatial join on those points, and you can get all of those into a flattened table or some kind of other method of pivoting it. And just by doing that alone, we reduced the number of points all the way from 52 million down to just over 600,000. So already a huge improvement in the number of features that we're working with. But the interesting thing about that is it also introduces a new problem, and that's adding a ton of attribute fields. And we know that it's not just the geometry that will increase our download size, but it's the attributes that can also have a very significant impact on that. So we got all the way back up to 1,200 fields just in that process.
One thing to just think about, like that reduction of the geometries is very important, because every geometry that the JavaScript API is going to work with needs to be processed and triangulated and managed on the GPU. So you want to keep that number as low as possible. I think for the attribute data, you have some more flex. We can easily keep the geometry on the graphics card and change the attribute data and get really good performance. But 1,200 fields is too much for the ArcGIS Online hosted feature service, isn't it?
It is, yeah. It's in fact they limit you to
1024.
1024.
Yeah.
And that's something I learned through
doing
very
this.
painful experience. But before we get into that, I mean, we decided to take it even one step further in the thinning. You know, and looking at this data in Pro, it became obvious that a 1/4 degree resolution was still too fine for what we really wanted to accomplish. If we're going to use a Spillhouse projection, that's a global projection. We don't want to have data that's too dense. So we could even make the resolution a little more coarse, down to 1/2 degree, and still work with it reasonably. So we
just on that point, it's very true. Like our end goal is a desktop browser at full screen.
Yes.
And to show the whole world, like Christian showed you at the beginning. And at a 1/4 degree, you didn't have enough pixels, so everything was sort of overlapping. So you would have to have a much bigger screen to be able to show it at 1/4 degree and show the whole world at one time. So we're not losing anything by reducing it to 1/2 degree resolution.
That's a good point. Yeah, when you have overlapping points in a data set like this, you're bringing down data unnecessarily. Doesn't make sense. So by running this, we did basically a select by attribute to filter out every 1/4. But I guess if the geometry ended in 1/4 degree or 3/4 of the degree, we filtered it out using that SQL expression you see there. And that reduced our number of points all the way down to 84,000. And that's something we know we can work with in a desktop. Even maybe pushing higher end phones, but for sure, desktop, we can work with this.
Just like we were doing 102,000 trees points, so easily 84,000 is good. And I'll say, when we did this, we were quite surprised at how well Pro worked with doing that expression.
Absolutely,
and,
yeah.
To help us manage that data. So, yeah, go Pro team.
Yeah. And so when we executed that filter, this is what the data started with, is the orange points. So you see that higher resolution, and then those blue points is the lower resolution. Lower resolution of the layer. So fewer points, but it's when you're zoomed out, you actually get plenty of coverage with a good deal.
So those are the 1/2 degree centroids.
These are the 1/2 degree centroids. So it was really unnecessary to keep those 1/4 degrees
definitely
in there. All right, but as Jeremy said, we have a limitation to the feature service, and that's, I wouldn't know that to call a limitation, but it limits you to 1024 fields. And so obviously 1,200 is too many, so I immediately chopped off about 300 just to get it publishable. And I was able to publish it with about 960 fields. And even, render it in the view by requesting a few at a time. I was able to verify that, we can indeed work with this layer. But that still had the problem of too much data. We can't render all 900 attributes of data in the browser at once. It's not usable. And so I started to query only for one attribute at a time. And what I mean by that is not just one field, it's one attribute for all those depth levels. So if I have 80 levels of depth now, for salinity, I'm requesting 80 fields. And then if I want to do salinity and temperature, it's now 160. So if I'm bringing down more than that, I'm basically setting a bunch of out fields on my query, makes it a huge query string, and then it makes it uncacheable, right? Because we can't use a GET request at that point. We're forced to use a POST once the query string goes over, what is it, 2000?
2048.
2048 characters. Yeah.
That's just the natural limit to the length of a URL that can be in an HTTP GET request. So anything bigger than that, most things along the internet won't handle it. So you have to move to a POST. POSTs are no bueno because they cannot be cached, like Christian said. So we lose out on any caching performance. And actually, this app that Christian has built, is an example of an app that could go viral. Maybe not viral definitely not viral on the phone, but viral on, imagine every school looking at this app. It's a great teaching tool, pushing that geographic information to the edge. And so it could be an example of an app that gets a lot of load. And then caching is so important there then because we want to be able to handle that load and not overtax the server resources. So POST no good. So how'd you solve that?
Well, I got on the phone with my buddy Keith, colleague here, and asked him, hey, what are some of the attributes in this data set that are most interesting to you? We've got obviously 12 per level, but if we don't need to render all of them, what are the ones that we want to work with? And he immediately said, well, temperature and salinity are two attributes that tend to go together. They have relationships, and I also wanted to explore relationships between variables. So I selected those two. I asked about the direction and velocity, and he indicated that was movement, and perhaps we could see patterns of currents if we were able to visualize that. So I was curious, and so I picked those 4 fields: temperature, salinity, velocity, direction.
I don't think you're going to show this, but Keith learned something, right? He didn't know that the data would be able to show that a Gulfist current in South Africa.
Yeah, I mean that's what was interesting. Is we already know what the currents are there, and I'm sure Keith is very, very familiar with that. But he got very excited when he saw some of those patterns emerge from this data set that he's already familiar with, and it was just a new way to look at the data. And so similar to reducing the geometries initially and then going even further by thinning them out, we got more aggressive with the attribute thinning. So rather than delete them from the service, you can actually create a new a view or a feature view of your feature service, and then limit or restrict the fields on that view. So you don't get rid of them, you still have access to them later. So I went through and selected only the ones I cared about, and that got me down to just over 300 fields, which we felt that we could work with in the browser. And not only that, we could request all of them at once using the star on the out fields, which makes that query string much shorter and therefore cacheable. And Jeremy already showed the max age, so I set that just so we can get as much performance as possible and get a data set that we can finally work with. And you already saw the app, but basically what's going on is, as Jeremy pointed out, rather than letting the API dynamically request those fields that are set on the renderer, we'd actually get a very poor user experience, because with every slider movement, every switch of the button, there'd be new fields getting requested, whether it's querying the service or getting it from the CDN if we've already gotten that particular tile request before. But it still would be a poor experience for the user. So we brought all that data down initially so they could have a fast experience. And that's just by setting those out fields in the layer to star. Now, that does come at a cost. When I didn't show loading the app, but you can see in this GIF here that I put a little loading icon, because it can take a few seconds for that app to query all that data and bring it into the browser. But once it's down, you can do some cool things and explore parts of the ocean that you might not be familiar with.
So that 280 megabytes, is that the size of the compressed query responses?
That is the raw data.
Raw data?
Yeah.
Do you remember what it was compressed?
Compressed, I don't.
I thought it was 280 compressed and then like 360.
Oh, you're right. Yes, yeah.
okay.
It was something like 360 or 390
Yeah.
uncompressed.
So 280 megabytes is a lot of data for a website.
yeah, it's definitely pushing it,
Yeah.
but still a cool app.
Yeah.
You can still do some cool things. So
We talked about it. We didn't. Christian didn't do this. We talked about potentially we don't need all the depth values,
Yep.
especially as you get for this data set as you get deeper in the ocean. I mean, they're not collecting it at a quarter degree at every depth level,
Yeah.
so you end up with a lot of points that are the same.
Yeah, so I mean, we just look at here for temperature. Once you hit, about 600 meters below the surface, the data gets less interesting, no matter what we're looking at. Even if we switch back over to salinity.
Yeah, you see that straight line basically there.
Yeah.
It's like you still want that data. So I think if we were to get rid of it or to make it smaller, as we would want the detail down to 600 meters depth, and then we'd want to, sample the depth values as you go further down. So we might, by just doing that, we might reduce each variable by, 20 fields.
Yeah.
And can get that initial size even smaller.
Yeah, or I mean, if say we're only interested in surface values, basically within the first 500, maybe 1,000 feet, we could potentially bring in another attribute like silicates or phosphates and see if there's anything interesting there. But still definitely bringing a lot of data in and pushing our limits here.
Yeah, probably a good version of this app would be just to 600 meters.
Yeah.
And then leave the surface alone.
Yeah. So yeah, that app basically wraps up the session. Just wanted to reiterate that the platform does a whole lot for you. Jeremy showed some pretty cool demos using the network tab on what the platform and the API does to optimize for you. But that also means that doesn't mean that you are absolved of any responsibility. You should do your part in making that data come down as efficiently as possible, especially if you're working with a huge data set like that EMU data. And those are some of the techniques we discussed. We didn't cover aggregation, but there are tools available.
Yeah, that's another great way to reduce the complexity for points or even lines and polygons. You just aggregate to a level of detail coarser. So another example of that tree data would be to aggregate that to, let's say, 100-meter squares or 100-meter hexagons. And when you aggregate, you can get the summary statistics of your attribute information. So I can get the average tree height or the tallest tree or the standard deviation of tree heights within a 100-meter cell. Or I could say I want to see what's the most common type of tree. So for within a 100-meter cell, what's the most common tree? What's the most common tree status? Are they diseased, not diseased? These are all patterns that, of course, you would do as a GIS person in using Pro to explore and understand the data. But that is also a tip for improving the visualization of data that you want to show when you want to show the entire region of the data. So that zoomed out view, aggregation can really help. And it's also going to be performant because you're reducing the features down.
Yeah, you don't necessarily want to see thousands and thousands of points when you're zoomed out. So aggregation is definitely a good thing.
I think the other thing, Christian, that you said that I think really is true is like we do a lot of things by default, but really it's up to you, the app developer, the web map author, to try different techniques to simplify the data even more so that you can get that better visualization. Of course, we didn't cover, we just focused on feature layers in this session, but there are many other visualization layers that you can create that will allow you to have lots of data. And probably the biggest thing would be raster tiles. Raster tiles, you can put as many features as you want in there because it's going to be a picture. I think vector tiles, you can maybe put a little bit more, but you can't put everything that you can in and a raster tile. Vector tiles have a limit on the number of features that can be in each tile, because it is actually similar to dynamic feature tiles. It's the at least the graphic of the feature. Then there are other tools like map image layers powered by map server. I think those also don't scale as much as the raster tile layers because they require a lot of processing on the server. They're also not cacheable, so you can only get so far with that. But we really see feature layers being the way that most applications are going to work with data going forward, because it allows you to build these hyper interactive applications like Christian's One Ocean app that you just can't get with like the raster tile approach. And so, embrace the feature layer and then just think about how you can make it faster.
All right. And with that, we want to thank you for watching and listening, and we would like to also request your feedback. If this content was relevant to you and you found it useful, please let us know. I'm active on GeoNet. Other team members are. You can reach out on GeoNet to us. Also, if there was content that you wished you had heard, we would love to hear what your requests are. If you have data that's large and you want to work with it, but this didn't quite help you in that effort, we'd love to hear what your use cases are so we can try to tailor the content more appropriately to you.
Yep. And while this was actually pretty fun to present in this recorded way, definitely can't wait till next year when everybody's back in Palm Springs for the Dev Summit and we can talk to each other in person.
Yeah, absolutely.
Thank you.
All right.